So we're in section 15. We'll get to learn some new terms and some new symbols in this.
What is that song?
The curl.
Oh.
So we'll get to learn today what the curl is. Some new terms, some new symbols. So that'll be fun. The other day, someone walked in here and looked at the board and they said, "Oh, vector fields. I hated vector fields." So far we've studied several kinds of functions. We've talked about just a function of a single variable where our input is a real number and our output is a real number. We've studied functions of multiple variables where input is multiple real numbers and our output is a real number. We talked about parametric equations where we get our input is a real number and we get several real numbers out, and that kind of led us into vector valued functions where our domain is the real numbers and our output is a vector. So an example of that would be a position, velocity, acceleration. Our parameter or our input was time, and we get a vector out. So a vector valued function assigns a vector to a real number. A vector field assigns a vector to a point in the plane or a point in space. So that's the distinction here, is a vector field assigns a vector to each point. And we write our notation for a vector field is we say f in the plane, f of xy, and we denote it as a vector, and we say mi plus nj, and or in the plane we say our function is of three variables, x, y, and, or in space I mean x, y, z. Plus pk, and our m, n, and p are functions of x and m and n are functions of x and y here. And m, n, and p here are functions of x, y, and z. So we plug in, we have a point in space and it assigns a vector. An example of a vector field would be a velocity field. So if you have, say, a fluid that's moving around, you can assign every point in that fluid a velocity vector. We talked about electric fields, so at each point in space there's an electric field that points a specific direction, has a specific magnitude. Gravitational field is an example of a vector field. At each point in space we have a vector, a force vector, that tells us which direction and what's the magnitude of the gravitational force. So those would be a couple of examples that might be familiar with vector fields.
So it's a slope field with magnitude?
Sort of. So we could get a slope field from a vector field, but it's a similar idea to a slope field. At each point we have a direction and a magnitude. The gradient back to our friend the gradient. The gradient is a vector field. Oh, that was tangent plane. So the gradient is a vector field. So the gradient's going to play a big part in chapter 15. So we have del. We defined the gradient of some function was f sub xi plus f sub yj plus f sub zk. So the gradient takes a point in space and assigns it a vector. So the gradient is going to play a big part in what we do in this chapter because of gradient. We can get vector fields from the gradient. Now to visualize vector fields, to sketch a vector field, to have an idea of what a vector field looks like, we can plug in numbers to our function, and that could give us an idea, and we can draw a bunch of vectors. The other way we can visualize a vector field is similar to what we did with level curves, and we look where the magnitude is constant. So one way to visualize, we look at constant magnitude. So that's one way we can visualize visualize vector fields in kind of a systematic way. So what I want to do, and again, this is kind of like visualizing level curves. So what I want to do is practice on this a little bit in your book on page 1063, number 1 through 6. They have some equations for vector fields, and we want to match the vector field with the graph. So let's look at those. If you don't have a book, get with somebody that has a book. And let me see if it's in this book also. So for the first one.
No, we're not ready yet.
Not ready? So the first one, f of our vector value function is x in the j direction. So if we think about this, think about where the magnitude is constant. Where is the magnitude of this vector going to be constant? When the x values are constant. So what kind of thing gives us a constant x value? A line, a vertical line. And so we're going to have vectors with a constant magnitude along vertical lines, and the magnitude is going to point. The vectors are going to point in the j direction. So which one does that match? C. So that matches C. So the second one, The second one is kind of the opposite. F of xy equals y I. So which one's that going to match? D. That one's going to match a D. It's constant magnitude on horizontal lines. So that one matches D. Number 3. Our vector valued function is xi plus 3yj. So where is that one going to have a constant magnitude? What kind of shape? A circle, a line, a plane, a hyperboloid? So to find the magnitude of a vector, square root of x squared plus 3y squared equals a constant. So x squared plus 9y squared equals some other constant, c squared. So what kind of shape is that? That's an ellipse. And our vector is going to point outward.
How do you know that?
So if you think, okay, we're on an ellipse and you pick a point, so it's going to point, say 1, 1. So it's going to point 1i and 3j. So it's going to point away from that ellipse. So which one does that match? B. That's going to match B. Number 4. Our vector valued function f of xy equals yi minus xj. So where is that one going to have a constant magnitude? At a circle, when we take the magnitude of this, square root of y squared plus negative x squared equals a constant. So x squared plus y squared equals a constant. And then from looking at this, which direction is our, if you plug in some points, you can figure out which direction your vectors point. So if you plug in point 1, 1, our vector is going to point 1i minus 1j. So which one is that going to match?
Okay.
What do we think? What's that? That shows a really bad point. How about on the axis? How about the point 0, 1? So at 0, 1, this is going to point 0i minus 1j. So which one does that match? E. So that's going to match 1, 0. So y is 0. I said 1, 0, right? So y is 0. So 0i minus 1j. Right? Okay. Did I said 0, 1? I thought I said 1, 0. Okay. I meant to say 1, 0. Now derive the mass of the sun, right, Andrew? All right, number 5. Number 5, we have xi equals, or f of xy equals xi plus sine yj. This one's a little trickier, because when we take the magnitude, we get some function of x and sine y. So Caitlin says A. And how did you? Why did you think that?
Because it's the most complicated graph. And this is the most complicated equation.
So the way I would look at this is I would say that the magnitude of the y component has to be between plus 1 and minus 1. And the magnitude of the x component gets larger as we move to the right, or smaller as we move positive or negative. So the x component is getting larger positive or larger negative. And we could also look at some points. At the y component at 0, at y equals 0, has to be 0. And the y component at y equals pi is 0. So we try to match up some of those points. And this would match up with A. We have a little more justification than it's really complicated. And then that leaves us for 6, leaves us with F. And if I were looking at F, finding the magnitude of this, we get a complicated function for the magnitude of that. The way I would look at this one was say that the y component is always positive, except when x equals 0, and then we have a 0 y component. And the x component is positive in quadrants 1 and 3 and negative in quadrants 2 and 4. So that would give you a way to visualize what this one looks like. And that would lead you to F on this one. So a couple of ways that we can visualize vector fields. Look at where the magnitude is constant. We can look at how the functions behave to help us see how these look if we're graphing them in the plane. Space vector fields a little more complicated, but the same kind of idea. Questions before we move on? All right, so now we're going to talk about conservative vector fields. Conservative fields are a particular kind of field that we like because they give us some nice properties that make them easy to work with. A conservative field, if our vector valued function is the gradient of some scalar function, and f has to be differentiable, then f, we call the vector field conservative. And we'll get to why we call it a conservative field in a little bit. Right now we're going to define this as a conservative function. So if our vector valued function is the gradient of a scalar function, it's a conservative vector field. And we call f, small f, our scalar function, small f is the potential function. So if you're in physics and you're talking about electric fields, the small f would be our potential, our electric potential. We could talk about our electric potential, our gravitational potential. Same idea. From the potential we can figure out our field. So small f is the potential function, our scalar function is the potential function, and our vector valued function is called conservative. And remember that del of some function, if we have f of x, y, z equals a constant, del f is normal to the level curves. And it's normal to the surface f of x, y, z equals a constant. So del f is going to give us a normal vector. So that's going to be one of the important properties that we use when we're talking about vector calculus, is that our gradient is normal to a level curve. So if we're looking for, if we have a scalar function, to find a conservative vector field for the scalar, for the potential function, all we have to do is take the gradient. So let's look at a quick example of that. So if we have f of x, y in the plane is sine 3x cosine 4y, and we want a conservative vector field, if our problem asks us for this potential function, so we want a conservative vector field. Our conservative vector field f of x, y, vector f of x, y, is just going to be del f. And when we take the gradient of this, the gradient of f is 3 cosine so if our partial with respect to x, 3 cosine 4y times the sine, hang on, I did something wrong here. So the partial of this with respect to x, what do we get for the partial of this with respect to x? 3 cosine 3x cosine 4y I plus partial of this with respect to y. So it would be a minus 4 sine 4y times sine 3x. So that would be our conservative vector field for this potential function. This should be J. That would be our conservative vector field. Capital F is the conservative vector field, and small f is the potential function. Now what we're going to be interested in, pretty straightforward, right? We just take the gradient of our scalar function. What we're going to be interested in is how do we figure out if we're given a particular vector field, how do we know if it's conservative? We want to know if our vector field is conservative. We're going to, the idea of a conservative vector field is going to be important. We want to be able to figure out when our vector field is conservative. So we have a test. So our test for conservative fields. If we have for a vector field in the plane, f of xy, some vector f of xy, and this is mi plus nj, it's conservative, or I'm sorry, yeah, it is conservative. If and only if conservative if and only if dm, the partial of m with respect to y, equals a partial of n with respect to x. And m and n have to have continuous first partials in an open disk. So we're looking at well-behaved functions here. This is true if f is conservative, f is conservative, then our vector field is the gradient of some potential function. And that tells us that m is the partial of this function with respect to x. In order to get my vector field, I take the gradient of f. And n is the partial of f with respect to y. And f of xy, f sub xy, is the partial of m with respect to y. And f sub yx is the partial of n with respect to x. And what do we know about the mixed partials? Mixed partials are equal. So if this vector field is conservative, it's the gradient of a potential function, and the partial of m with respect to y is the second partial of our potential function, and the partial of n with respect to x is the second partial of our potential function, and those two have to be equal if we have well-behaved functions. So this is our test for conservative fields in the plane. The partial of m with respect to y has to be equal to partial of n with respect to x. So our questions, the questions about conservative fields are going to say, is the vector field conservative? And then we want to find a potential function. So everybody good with how we figure out if we have a conservative field? All right, so let's look at a question, an example involving this. So we want to know, is this vector field 3x squared y squared I plus 2x cubed yj, is this conservative? And if so, find a potential function. So we want to test whether this is conservative. So for this vector field, we're going to say that m is 3x squared y squared, and n is 2x cubed y. And we want to take the partial of m with respect to y. So partial of m with respect to y is 6x squared y. Partial of n with respect to x is 6x squared y. So yes, the field is conservative. Now we want to find a potential function. So how are we going to go about finding a potential function for this? Anybody have an idea? Well, we need to find a function, a scalar function, such that when we do the gradient, we get these two things. So we have to integrate. We need del f equals our vector field. We need this. So the other way we could say that is df dx has to equal m and df dy has to equal 2x cubed y. So we need to integrate, but we end up with a system of differential equations. Now most of the problems that you're going to have to do this way are pretty nice, but we end up with a system of differential equations. So our function f has to equal the integral of df dx dx. Yeah, we're plugging this function in here. So that has to be the integral of 3x squared y dx for my first equation. And we're going to have an integral for the second equation as well. So when we integrate this with respect to x, what do we get? X cubed. Did I miss? Yeah, this should have a y squared. I missed that here. So this should be x cubed y squared. But my constant of integration, what is my constant of integration going to be? We're taking the integral with respect to x, but we have a function of x and y. My constant of integration can be a function of y. So my constant is some function of y that we have to find, because y is constant with respect to x. My constant of integration can be a function of y. And we need to find that from our conditions here. And we also know that f has to equal the integral of df dy with respect to y. So that's equal to the integral of 2x cubed y dy. And when we integrate that with respect to y, what do we get? We get x cubed y squared. And our constant of integration can be a function of x. Now when we take the partial of x cubed y with respect to x, what do we get? We're taking the partial derivative. 3x squared y squared plus whatever the derivative of this is with respect to x. Well, all we need is 3x squared y squared. And when we take the derivative of this with respect to y, what do we get? 2x cubed y. I think we did the oh, I forgot. Let's see. Did you so yeah, that's what we need. We need 2x cubed y. So all we need here is 2x cubed y plus whatever the derivative of this is with respect to x. So when we take our derivatives, our partial derivatives of this function, we get our vector field. So our constant doesn't vary with x or y. So f is x cubed y squared plus just some constant. Because when we take the partial with respect to x, we get m, and when we take the partial with respect to y, we get n. If our function were more complicated, we would have to take into account some function of x or y to make sure that when we take the partial derivatives, we get our m and our n. Questions on that? All right, so to have a conservative vector field, it has to be the gradient. Our vector field has to be the gradient of some potential function. If our function is conservative, we can integrate to find our potential function. But when we integrate, we have to make sure we're taking into account that our constants of integration can be a function of our other variable. All right, have a little bit more to talk about. I warned you earlier we had a lot to talk about today. The curl. We want to talk about the curl of a vector field. So we know what a vector field is now. We know what a conservative vector field is. We know how that a vector field comes from a potential function. We want to look at this new quantity of a vector field called a curl. So if we have some vector field in space, our vector field of x, y, and z, and that is mi plus nj plus pk, then the curl and we write curl f that equals del cross f. Just del cross f. And we're treating del is a differential vector operator. So we talked about del as an operator before. It doesn't make any sense by itself. It has to operate on something else. When we take the gradient, it's operating on a scalar function, and we take the first partial with respect to x. That gives us our I component of our vector. Partial with respect to y gives us our j component. Partial with respect to z gives us our k component. Now we're forming the cross product of del with another vector. And we said that del, we can think of del as the operator d dx I plus d dy j plus d dzk. So this doesn't make any sense standing on its own, but del cross f, if I form the cross product of this operator with a vector, so del cross f, we can figure it out by this determinant. So this is how we figure out the curl of a vector field. Take the cross product of our del operator with our vector field. And we say that if del cross f equals 0, we call f irrotational. And we're going to have to wait. We're going to have to wait until the end of the chapter, almost the very end of the chapter, to to give kind of a physical interpretation to the curl. Basic idea is the curl tells us the tendency of a vector field to cause rotation. And as we get further into the chapter, we will have a stronger idea of what that actually means, because we're going to be integrating the curl over surfaces, and that's going to tell us something about our vector field. So the gradient going to play a big role in chapter 15. The concept of the curl is one of the main ideas of chapter 15. We're going to use this quantity, the curl, to do a lot of different things with vector fields on surfaces. So we want to figure out what we're shooting for is we're going to talk about adding the curl up over the surface bounded by a specific region. So that's how we end up with our multiple integrals in here. So let's look at an example of finding the curl of a vector field. And then we have one last topic to talk about. So we want to find the curl. So our function is x squared zi minus 2xz j plus yzk. So we want to find the curl at a point at 2, negative 1, 3. So to find our curl, we're going to set up our determinant. Our curl is del cross f, and that is our determinant of our components of our del operator and our vector. So this is x squared z minus 2z and yz. Very easy to make a sign error when you're calculating the curl. So you need to be very careful when you're calculating the curl. So our curl is going to be I times the quantity. If I'm looking at d dy of yz, which is z, minus d dz of minus 2z. So that would be plus, and I wanted this to be 2xz. So this should be a 2x here. So this would be minus a negative 2x. Minus j times d dx of yz, which is just 0, minus d dz of x squared z, which just gives us x squared, plus k times d dx of minus 2xz, we get minus 2z, minus and d dy of x squared z, which is 0. So finally we get 2x plus zi plus x squared j minus 2zk. And del f at our point, or del cross f at 2, negative 1, 3. We're just going to plug in, and I get 7i plus 4j minus 6k. And again, our curl, just as a kind of guideline, this tells us the tendency of this vector field to cause a rotation at this particular point. And we'll have a better understanding at the end of the chapter what that tells us, what that means. Questions so far? All right, so vector field. Vector field assigns a vector to each point in the plane or each point in space. A vector field, we can visualize a vector field in a couple of ways, looking at where the vectors have constant magnitude, or we can substitute some points in to get an idea of the behavior of the vector field. A vector field is conservative if it's a gradient of some scalar function. The scalar function is called the potential function. We had a test for conservative vector fields in the plane. If we take the partial of our x component with respect to y, and it's equal to the partial of the y component with respect to x, then our vector field is conservative, and we can find a potential function that gives us that vector field. So we're going to look at this test for conservative vector field in space. So the first test that we used works for vectors in the plane. We're just looking at the two partials of the x component and the y component. If we have a space vector, it's a little more complicated. But now that we know about the curl, we have a little easier way to write this out. So our vector field is conservative if and only if have you guys seen the shorthand here for this? If and only if? No. No? Yeah, you put two F's. This means if and only if. When I did analysis, we use this all the time. If and only if. If and only if the curl of f is 0. So if our curl is 0, then our vector field is conservative. And this is equivalent to the condition that gives us our curl equals 0 is dp dy equals dn dz. dp dx equals dm dz. And dn dx equals dm dy. So this last one is the one that if we just have a vector field in the plane, this last one is the condition we had for a vector field in the plane. These other two come from our other two components. And if we calculated out the curl, these are the partial derivatives that have to be equal to give us a curl of 0. And the reason is exactly the same, because our mixed partials have to be equal. The mixed partials being equal is what gives us these conditions. And just like we did in the plane, if our vector field is conservative, we can find a potential function for the vector field. So if our vector field is conservative, we can find a potential function. So let's look at one final example. So if our curl is 0, we have a conservative vector field in space. So we want to know, in this example, is f conservative? And our vector field is y squared z cubed I plus 2xy z cubed j plus 3xy squared z squared k. And we want to know, is this conservative? And if so, we want to find a potential function. So to figure out if this is conservative, we have to find the curl. We're going to find the curl. So we're going to say, we're going to form our determinant, del cross f, equals our determinant, I, j, k, of y squared z cubed, 2x y z cubed, and 3x y squared z squared. Sorry, this is my partials go here. I got one row ahead of myself. ddx, ddy, ddz. And now my components of my vector field. And if I form my cross product with my function here, I end up with that this does in fact equal 0. And I should go back here. I realized here when I wrote this down, if del cross f equals a 0 vector, 0 and the 0 vector are not the same. 0 is a scalar, and the 0 vector is a vector. So this is a vector that has no magnitude. So the magnitude of the curl is the scalar 0. So our curl is 0, so f is conservative. So we can find a potential function. To find our potential function, we have a system of 3 equations, 3 differential equations that we need to solve. So for our potential function, let's say that f is our potential function. And we know that the partial of f with respect to x has to equal our x component. So that has to equal y squared z cubed. This gives us the equation, the integral of y squared z cubed dx. And that equals xy squared z cubed plus some function. This is the partial with respect to x, so plus some constant or function, some function of y and z.
Why is x squared? It's not.
Sorry, this should be x. Thank you. Plus some function of y and z. So a function of y and z can be constant, constant with respect to x. And our partial with respect to y equals 2xyz cubed. Has to equal 2xy z cubed. So we get the integral of 2xyz cubed dy. And that gives us x, y squared, z cubed, plus some function of x and z, which is constant with respect to y. And our final equation, our partial with respect to z, has to equal 3xy squared z squared. So we get the integral, we integrate this with respect to z, and we get xy squared plus z cubed plus some function, thank you, xyz cubed, plus some function of x and y. And if we take the partial of x, y squared, z cubed with respect to x, we get y squared, z cubed. If we take the partial of x, y squared, z cubed with respect to y, we get 2xy, z cubed. If we take the partial of this with respect to z, we get 3xy squared, z squared. So our constants don't have any dependence on the other variables. So our function behaves nicely. So our potential function is xy squared z cubed plus some constant, just a scalar constant. That's our potential function that gives us our vector field. And the reason we're spending time talking about potential functions is when we have a conservative field, conservative fields have special properties that we're interested in this chapter. They give us they behave in specific ways that we'll talk about a little later when we start talking about integrating vector fields. Conservative fields have some nice properties that we want to. If we have a conservative field, it saves us a lot of work. And fields and potentials are a big topic when you start talking about electromagnetism, when you talk about gravity, when you talk about fluid dynamics. Fields and potentials play a big role in those kinds of things. All right, any questions? Okay. Homework. And let me look at something really quick. Okay. All right, there you go. That was a lot of stuff, and we're not even done with the first section. Tomorrow we're going to talk about the divergence of vector fields. So this first section is really laying the foundation, laying a big foundation.